Okay, the first part of question 3 is just quite a clever little question, just saying how could you use a single pH measurement to show that this acid, propanoic acid, is a weak acid rather than a strong acid. We've got this solution with a concentration of 0.1 molar, and the way to think about it is to say, well, if it were strong, we start with the strong acid case because that's the easy one where we can easily calculate what the pH was. So if it was strong, then every single molecule of that would break up to give an H plus ion and a propanoate ion, and therefore the concentration of H plus would just be the same as that because all of it would have broken up to form H plus. And then you say, okay, well, if I know the H plus concentration, I know what the pH would be if it was strong, because so I can say, so pH, which is minus log to the base 10 of the H plus concentration, if you take minus log of that, you get, it would be 1.00. Okay, so if it's not equal to 1, that suggests it's a weak acid, but you've got to go slightly more than that and say, well, would it be more or less than 1? So we say if it were weak, then the H plus concentration would be less than 0.1. Okay, because not all of it would have ionized, so there'd be less H plus than you'd get in the strong case. And if you take minus log to the base 10 of a value that's less than 0.1, you get a value that's bigger than 1. So you get, so pH would be greater than 1.00. And so you just measure the pH for that solution, and if you get a value that's bigger than 1, that proves it's a weak acid. Next step is to move on from that and show how you would actually calculate the value of Ka for that weak acid. So Ka is a hugely important number in weak acid chemistry. So the first thing to do is to write down its definition. They've given you the equation for the ionization, and Ka is just the equilibrium constant for that ionization. In other words, Ka is equal to H plus times the propanoic concentration divided by propanoic acid. And in any weak acid question, that definition of Ka is likely to be important and therefore is likely to need to be there to get you a mark. In practice though, in this case, you can't use it directly to get the value of Ka because there are too many variables there that you don't know the value for. So you have to make the approximation, which is that so long as you've got a weak acid on its own in solution and you haven't added any extra salt, any extra of the conjugate base to it, then you can say every time you make an H plus, you make one of those as well, just by dissociating the acid. So the concentrations of those will be equal. So we can say that's approximately equal to H plus squared over the acid concentration. And then all you have to do is to explain where you get those two numbers from, and you've got your method for calculating Ka. So you just say H plus is equal to the inverse log of minus the pH. Okay, so we had earlier on that pH is minus log to the base 10 of the H plus concentration. Well, if you do the inverse of that, inverse log of minus the pH gives you the H plus concentration. Mathematically, that's the same as 10 to the power minus pH. And you can remember it in either of those ways and write it down in either of those ways. But you need to have something along those lines to explain where you'd get the H plus from. And the concentration of acid, well, you just use that number. You ignore the fact that a small proportion of it has ionized, and you just say, we'll assume that the concentration of the unionized form is just the total propanoic acid concentration, so it's 0.1. So you just get, so Ka would be equal to H plus squared, calculating H plus like that, divided by 0.1. And that's your answer. Okay, part B now is shifting attention to an alkali this time. And what you need to remember is that if the pH question is about an alkali or indeed about water, that the magic number you need is Kw. And that's what's going to come in here. But the first thing we have to do is to recognise that again we're starting with pH. Before we can do anything with that, we've got to turn it back into the H plus concentration. So similarly to in the previous question, we start with H plus is 10 to the minus pH, or inverse log of minus the pH, which is 10 to the minus 13.46, which comes out as 3.47 times 10 to the minus 14 moles per dm cubed. Okay, that's the H plus concentration. What we're interested in is the OH minus concentration, and the number that relates those is Kw. So Kw, you've got to learn the definition, is H plus times OH minus. And it's called the ionic product of water, and its value, remember, is on your data sheet. It's one of those numbers that's on the back of your periodic table, and you must remember that. So we know that from the data sheet. We know H plus because we've just calculated it, so we can solve for OH minus. Okay, so we get Kw divided by H plus is equal to OH minus, which is 1.00 times 10 to the minus 14. It's off your data sheet. Divided by 3.47 times 10 to the minus 14. And if you work that out, that comes to 0.288 moles per dm cubed. And that's actually the answer, because that's the concentration of OH minus, but that's the same as the concentration of NaOH, because each mole of NaOH is made up of a mole of Na plus and a mole of OH minus. So that's your answer, because that's the NaOH concentration. Okay, now part C is a buffer question. This is a good example of the kind of waffle you're very likely to have to put in for a buffer question. So make sure you revised it thoroughly and that you can reproduce this kind of answer confidently. So the first thing it asks you to do is to explain why you get a buffer solution when you mix excess propanoic acid with sodium hydroxide. And the key to that is you're going to have to write an equation for propanoic acid reacting with sodium hydroxide. So remember, it doesn't matter that it's an organic acid, it just does the same as any other acid. Acid plus alkali goes to salt plus water. So your equation is going to be, there's the acid, plus NaOH, and the salt is simply what you get when the H plus ion from the acid, which is going to be that one, is replaced by the sodium ion. So you get CH3, CH2, COO, Na, plus water. And that's it, it balances without you needing to do any more than that. So that equation needs to be there to explain that when you add excess propanoic acid, some of it will react with the sodium hydroxide to form that salt, but that because the propanoic acid is in excess, there will still be some of it left unreacted as well, because there wasn't enough sodium hydroxide there. So the mixture you have at the end will contain that salt, and therefore will contain the propanoate ion, because remember, salts are ionic compounds, so they're fully ionized. So it will contain that ion, but that's in excess, so some is left at the end. And so what you have is a mixture containing the acid and its conjugate base, and that's what you need for a buffer solution. So explain that. And then you've got to explain how it works. So it says, how does it control pH when acid or alkali is added? Now the key to that always is to write down the ionization equilibrium. It's already there on the previous page, but you need to write it down again so that you can talk about it in Le Chatelier terms. And in general, remember, in buffer questions, that's all you need, is to remember that it's about the ionization equilibrium of the weak acid. So you write that down, and you say, okay, in our mixture, remember, we've got lots of this and lots of that. So the equilibrium can shift in either direction because there's plenty of stuff on both sides to let it do that. So if we add acid, what's going to happen? Well, the H plus concentration will increase, but Le Chatelier tells you that the equilibrium will respond to that by shifting to the left to oppose the change and use up most of the acid that was added. So you need to do the Le Chatelier thing and say that the equilibrium shifts to the left to oppose an increase in H plus. And then again, because the question says you've got to use equations, we've got to just say, well, what is that reaction when it shifts to the left? In other words, we've just got to write out the back reaction and say, i.e. CH3, CH2, COO minus reacts with H plus to give you propanoic acid. So that's easy. That explains how the buffer solution copes with the added acid. With added alkali, it's just slightly more tricky, because when you add alkali, you're adding OH minus, and there is no OH minus in that equation, so you've got to explain how it's relevant. And the relevance is that the OH minus that you add reacts with H plus, and again, write the equation for that. Dead easy equation is just OH minus plus H plus reacts together to make water. But you should write that down as part of your answer to explain why this substance affects that equilibrium, because the effect of that is that H plus drops, but if the H plus drops, this equilibrium will shift to the right to oppose that. So you say, so the equilibrium shifts to the right to oppose this. And then again, just spell that out in terms of this equilibrium. In other words, it's just the forward reaction, i.e. CH3, CH2, COOH goes to CH3, CH2, COO minus plus H plus. And that's actually all you need to get all the marks. Although what you could add, and you probably ideally should be aware of this, that is that if you combine those two equations, in other words this one, OH minus plus H plus going to water, and you look at the combined effect of that with this reaction, you can get that the overall response to adding OH minus is that the H plus cancels out because it's on the left in that equation and the right in that equation, and you get this. Okay, propanoic acid plus OH minus goes to propanoate plus water. Generally speaking, if you can't easily see how you arrive at that equation, although it's quite easy, you just add those two equations together, but you wouldn't need that one, so don't worry too much about struggling to remember that one. The important part is to remember that to explain how acid works, and that to explain how it works with alkali. Okay, that's it for part C. Part D is doing the Brunstett-Lowry thing. So you just need to learn this. It tends to be sort of self-contained, you know, you either think about acids in the Brunstett-Lowry way or in the simple way, and if it isn't either mentioning their names or talking about conjugate pairs and things, then you don't really need the Brunstett-Lowry approach. But here you obviously do, because it talks about conjugate pairs. So we've got HNO3 plus propanoic acid in equilibrium with something plus something. Now, what that means is that although these are both normally acids, in this case one's going to function as an acid and the other's going to have to function as a base. And what you're supposed to do is to recognise that that's a strong acid, Remember, you've got to learn that nitric and hydrochloric are strong acids. So that's a strong acid, that's a weak acid. So in the trial of strength as acids, nitric acid will win. So that will function as the acid, and that will function as the base. Which means that nitric acid, if it functions as an acid, remember that's a proton donor, so it will lose H+, and that will give you NO3-, and that's straightforward. This one will function as a base, which means it will actually gain the extra H+. And you think, well, where do I put it? But you just stick it on the end. So you get CH3, CH2, COOH2 plus. And don't worry about the structure of it. Just think, well, if that's acting as a base, it will have the extra H+ in the formula, and so you get that. And then you've just got to complete it by identifying what's what on this side in terms of acids and bases. So NO3- is obviously the conjugate base of HNO3, because the conjugate base is what you get when the acid has lost its H+. So that's the base, and it tells you to label them as pairs. So you can either join them up like that, or call that acid 1 and base 1, and this base 2 and acid 2. Because this obviously is an acid, because if it goes in the reverse direction, it donates the proton. And so those are the other pair, base 2, acid 2. And finally, we've just got a bit of equation writing practice. So propanoic acid with magnesium. Again, it's just a reminder that you've got to learn those essential reactions of acids. You know, acid plus alkali, acid plus oxide, acid plus carbonate, acid plus metal. They're all fair game, just as they have been in every exam since year 10. But, you know, you're much more likely to get some unusual acid or base now than, you know, rather than just HCl and sodium hydroxide. But the recipe is the same. So acid plus magnesium goes to salt plus hydrogen is what you need to remember. That's the general recipe. And if you're not comfortable doing that, quite a useful trick is to remind yourself what HCl would do. Okay, so this obviously isn't the answer to the question, but if you remember, you have magnesium plus 2 HCl goes to MgCl2 plus hydrogen. And you just got to think, well, if I have propanoic acid instead of HCl, it will do the same thing. So I get magnesium plus 2 moles of propanoic acid. Okay, so following the same thing, just with a different conjugate base, Cl- compared to propanoate, will give you the salt plus H2. Now the salt this time, when that loses H+, it will give you CH3, CH2, COO-, and you'll need 2 of those to balance the Mg2+, just like you needed 2 chloride ions to balance the Mg2+ there. So the formula looks complicated because you need 2 propanoates and a magnesium, but you can see the relationship. You've got magnesium ion and 2 chloride ions, magnesium ion and 2 propanoate ions. It's the same thing. So use that as a guide, and it tells you what's got to go on here, plus H2. And then you can obviously scribble that out or whatever to make it clear that that's the answer to the question. Then you've got to write an ionic equation for the reaction of aqueous propanoic acid with aqueous sodium carbonate. This is an important issue that when an acid reacts, it's generally going to be the H+ ion that reacts, and the other one in all these acid-base reactions just acts as a spectator. It's not involved. So in this case, the ionic equation has magnesium, and the propanoate bit is irrelevant because the propanoate ions are still there at the end, so it just has 2 H+ from there. And what do they turn into? Well, the propanoate ions are still there, so they are obviously not going to appear, but the magnesium has changed because it's now become Mg2+ and hydrogen. Okay, so what I've done is edited out the propanoate ions because they were unchanged in the reaction. They were spectator ions. And you probably don't need the state symbols, but usually in ionic equations you put them in. So the magnesium is solid, the ions are aqueous, and the hydrogen is a gas. And that's the end of the question.